for the introduction. It's a pleasure to be here. Just wanted to say something. I'm working as a camera software engineer. I do research, but my title is software engineer. And I'm working at the company that developed a machine learning language that can learn new languages without being trained on those languages, right? So yeah, I'm working at Google camera team. I'm not sure if you are aware about Pixel devices, but we have Pixel devices. And before that, I was working at Apple, um, both working on color production and correction. So today I'm gonna talk about camera ISP, and I will focus on color perspective. Like I will talk from color perspective more than the other parts. I will start with the camera image signal processor, which is camera ISP, how the camera process the frames and show us these beautiful images we used to see. And then I will talk about post-capture processing or off-camera ISP pros and cons. Maybe that's something interested to people who are working on high-level computer vision, because like there is some advantages of working on like on the early stages of the camera ISP before taking the final JPEG images. And then I will talk about the learnable camera ISP, the trendy part nowadays, and then how to make that more practical. So I will start with the camera ISP, and what we see as end users is completely different than what the camera sees or the camera ISP start with. And there is a journey to go from this image to this image, right? So this is the first stage the camera ISP starts from, and then there is a journey to go to final one, and this journey applied per frame. So I just wanna just to confirm that you got it. When I open my camera here, every single frame shown, there is a lot of processes I will discuss. There is no standard ways, but like the general flow. And that happened for each frame, like 30 times per second, for example. So we start with what we call mosaic row image. And if we have a closer look at a single patch, small patch from this image, you can see this dot pattern in this image. It's a single channel image. There is no RGB here. And this is a very dark one. And we have this dot pattern. And this dot pattern actually comes from the way the image formulated. So we have the incoming light to the lens, and that's like whatever reflected from the scene to the lens. And we have the camera sensor, which is the device that's responsible to convert the incoming light to electrical signals. And on top of that, we have what we call the color filter array. So the color filter array is something that try to filter out some unwanted signals for each cell and focus on a certain bandwidth from the visible light coming for this scene. So one focus on red wavelength, one for green, one for blue, and that will give you these three patterns. And when we merge together, we will get this dot pattern. And each dot here represent one of the color information, the RGB, right? And the raw image here is linear representation of the incoming light. So you have a perfectly linear, or not perfectly, but like approximately linear representation of the incoming light of that particular scene. So start from the mosaic raw image, and then we have lens shading correction that try to focus what we called lens shading phenomena, where we have in the middle, we have brighter values than the edges in the received image, and that caused from the way the light transfer from the lens and hit the sensor from different angles. And this step just try to improve or like uniform the brightness level of the image. And then after that, we have demosaicing, where we start from this pattern and the goal trying to complete what's missing, right? So the simple way to do that is just like interpolation, right? You have some information here and you try to guess the missing parts. So that gives us the RGB image, and then now we have colored image, but this colored image is very greenish. So if you are interested in photography and you know like what the meaning of like raw images or DNG files, and like you use Lightroom to edit your photos. So this is what we call raw image or RGB demosaicked raw image. And we have this greenish tint. Why that happened? Because of the way we formulate the image. We have incoming light from the light source and reflectance from objects. And we have the camera response function that like formulate the mosaic row values. And we usually have a peak in the green bandwidth. And that like result in a bias toward the green color more than the others. Then we have denoising. So if we have a closer look, we will see a lot of unwanted variations in brightness and colors in the image, and that's what we call noise. So the goal, trying to remove that noise. You can think about it like we can implement it in a very simple way, like using median filter, and we can go until the deep neural network stuff, like we have an like deep network that denoise the image. So we remove the noise. So we have the denoised raw RGB image. And then we have the AWB stage where we are trying to do the automatic white balance correction for this image. So you can see the difference between before and after. And auto white balance correction mainly trying to remove the this kind of bias or unwanted bias in the image. So it includes the bias, the greenish part here, and the color of the light source. So we try to remove that with the auto white balance correction. And then right now we have the white balanced raw image, and this image in a non-standard color space, which means like if we have two different cameras and we capture the same scene, we will observe different values. So the goal right now is to go to standard space, right? So this is the step what we call color transforms, is color space transform. And that take us from the white balanced raw image to a linear sRGB color space. And we have different standard color spaces. Like it's optional to go with, to any of them. So one of them is linear sRGB, and the other one that's perceptual color space called CIEXYZ. And I will go into details how we can go to those standard color spaces. So let's have a closer, like discuss in more details how the step of white balance is done, and then going to the standard color space. So let's go with the white balance. We have denoised raw linear RGB image, and our goal is to have this image. So very simple. We have two stages. The first stage is called illuminant estimation. So we try to predict the RGB, like just a single vector that represents the illuminant color in the current scene. So that has an assumption that we has a single light source, because like our goal trying to remove the bias and the light source color, right? So we just predict a single global vector, just three numbers. Once we have that, we apply a linear diagonal correction matrix. So go ahead. What sorry? Why the goal is to white balance? Because without white balance, we will have this image. Yeah.
I think that's a goal.
That degradation in the image. Yeah. So it's just like it's one of the steps that we are doing to improve the image and get the very fine, beautiful image at the end.
Information we need to have whatever algorithm that you use to be able to find certain information.
I didn't get it. Can you ask it again?
So what I'm trying to comprehend here is there's predefined, predefined ways to do this, what you are doing, but doesn't say what information you're trying to get.
To get?
Yeah, let's say there's something underneath this bench.
Okay.
Can we guarantee that doing white balance raw image can make that
Is that
thing more
better
visible?
or
Yeah.
visible?
Yeah.
So basically, the
Mm.
okay. So what I'm saying right now is the standard, not the standard. Sorry, the common practice in industry, right? Or like in academia, even discuss like any person follow the standard camera ISP. We do that in this way, right? Some of them, some of the steps are not perfect, like this one. Like we assume it's just a global vector. But if we are interested in doing that perfectly, then we need to do white balance especially, right? Like if we can correct this differently than this part, right? And for what you are saying, this is kind of a specific maybe or use case of the camera SP where you can customize your camera SP to maybe improve the visibility of whatever, like dark regions, right? But I don't think this is related to white balance. White balance just adjust the chroma values, not the intensity. But we can do that later in like later steps I will discuss, okay? Okay. Yeah. Like the goal by definition, we try to remove this. And some of users will hit that. And usually in production, like in industry, we don't follow the academic definition. So the academic definition try to remove any color, but in industry we try to just remove the light color in outdoor scenes, but keep a little bit in indoor. And that's why when you take any photo indoor, you can see this kind of yellowish light color still in the image, right? But if you run an algorithm from academia, it will just make it white. So just remove it, right? Yeah. So yeah, so this is these two steps of auto white balance correction. Very simple. And I will just go into details of one of the simple algorithms that doing the illuminant estimation. It's just gray word saying that if we take the average of the image, we can estimate the illuminant vector that we would like to remove. So just one line of code, right? So let's do that. So this is the gray world result with this scene. And this is the final image after rendering it through the rest of the camera pipeline that I will discuss. It looks great, very simple, one line of code, but it doesn't work for all examples. Like we have many corner cases that can break this simple gray world. So for example, like this scene, we have the dominant color is not what we try to remove. Like we have the dominant color of the object itself, like the apple. So gray world remove a little bit or maybe a lot of the original color of the object as well, right? So to understand how bad the gray world is, let's see the image, the same image, but if we correct it properly with white balance. So here it is. So you can see this if you do white balance correction correct, and this if you have some errors in white balance. So gray world is one of many methods that what we call statistical methods. They are based on some assumptions, like the gray world saying, yeah, the average color of the scene appears achromatic, or like that represent what we try to remove. Gray edge is saying the average color of the edges is achromatic, and so on. But most of them are very simple, one line of code, but can fail in many scenarios. So then we have the learning methods, right? So many methods, and the scheme is very simple. Give me training data, and the ground truth. In our case, the ground truth is the RGB values that represent the bias in the scene that we try to remove. And then we train it, and at testing, we just use the same model. But so this kind of methods usually try to map from input image colors in row space, linear space, to the distribution of the illuminant color produced by the camera, right? So we usually train that for a single camera, not just a mix between cameras. And we typically use angular error to like minimize the loss function. So just like very close to the cosine similarity, right? Like it's just a dot product between the estimated vector of the color and the ground truth one, right? And Yeah, many methods proposed. Some of them rely on the image, some of them rely on the histogram that represent the colors, since we are not interested on the semantic information that much in this problem, right? We're just interested in the color, and we try to remove the color bias. And some of the methods go beyond this single image assumption. So, for example, Abdelhamid in CVPR 21 proposed to use two different versions of the scene, each one captured by one of the cameras available in smartphone devices. And from the two images, they extract a small feature and then feed that to an MLP to predict the illuminant color in the scene. And we have other methods use depth estimation in addition to the RGB images to improve the quality of the illuminant estimation. And we had a paper accepted the CVPR. So we proposed to use the long and short exposure frames in HDR imaging, uh, available already on most of the cameras. And we extract some features and feed that to a neural network to predict the illuminant color. I will not go into details here. I just give a very overview of what we have. But in all those methods, we have a major problem, which is if we capture the same set of scenes, for example, 200 images with different cameras, and measure the ground truth for those 8 cameras, we will observe different distributions. And why that happened? Because of the way our raw images, which is linear representation of the incoming light, is formed. So we have the illuminant spectral power distribution of the light in the scene. We have the scene object spectral reflectance, and we have the camera response function. These 3 curves I discussed before. So every camera has a different camera response function. That means if we measure the RGB values from different cameras of the same object, we will get 3 different RGBs, right? And that means we have different ground truths, right? So that's for now about white balance. And then let's go to the second step, how we go from white balanced raw image to linear sRGB or one of the standard color spaces. It's very traditional, simple calibration step. So we have we are doing that by multiplying the RGB colors with a global 3x3 matrix. It's just a linear transformation of the colors. And we do that by capturing a standard color chart, for example, this one, under a certain lighting condition in RAW of this particular camera. And then we already knowing the target colors in the standard space. Then we fit a 3x3 matrix to map from the white balanced color to the target colors, and then that give us the matrix. And by capturing the same color chart under different lighting conditions, we will get different matrices. And at inference phase, when we capture any scene, we look into what lighting condition corresponding to the matrix, and then we pull it up and use it to map to the standard color space. So it's kind of, sorry. Oh, go ahead. Oh yeah, like this color chart is very expensive, like at least $600 maybe, and they just have like a very flat surface of colors, right? So why it's expensive? Because they measure the corresponding standard colors in one of the standard spaces, right? So you capture it in linear, and then you measure that manually maybe, and then extract the values from the image, and then you do the fitting, right? And we do like you can think about it as like a set of linear fittings. And because of the mapping from raw to the standard space is not linear, so we do that like by dividing the problem into small problems, right? So, and then after that, we have local tone mapping that take us from this image to this image. You can see the differences. So it just enhance the local contrast of the image. And then we have a global tone mapping that enhances the global tonal rendering of the image, and more and more and more of operations including lookup tables, like 3D lookup tables that just manipulate the colors. Why? Just that's like we try to improve the colors in certain ways based on some certain criteria, right? So, and then you get the final image. And that, all of that happen every frame. Every frame, you just open your camera even before capturing, all of that happened. And I just want to highlight that there is no standard camera ISP. So that means some companies will say, okay, I will do the denoising here maybe, or maybe I will do here and here, right? Like, and every company doing whatever they see is better. And I would like to highlight that we have two different groups. The first group is a set of operations that are linear and camera dependent, which mean if we change the camera, we need to tune that. And the tuning is a lot of money, like big teams just doing tuning for each camera every year. And we have the nonlinear, which is less dependency on the camera, which is starting from here. Because once we do the color space transform, we are in standard space, right? So whatever you train on your network to do the local tour mapping, you can plug in it and play next camera, right? And finally, I just want to say every single block here is a research problem, and we have many, many papers under that, right? So to conclude, based on this discussion, I think that justify why we can observe different colors for the same scene if we capture with different phones, right? Uh, maybe we can do, but maybe you will not see it. But I have two phones. I can show you an example. So Pixel versus iPhone. So you can maybe see, no, I don't know. You can see like this one is greenish and this one is not, right? Like if I moved here, this is more blue, like reddish, etc. Right? So you can try it. And that's because we have different blocks, we have different algorithms, we have different sensors, and that's why most of the computational photography methods, at the beginning at least of the research direction of that, focus on post-capture processing instead of tying themselves to the camera-specific things, right? So let's just forget about that and let's give me the final JPEG image and I will enhance it, right? So we have denoising work on post-capture camera ISP, off-camera ISP, and we have reflection removal, and we have whatever, like image deblurring, image enhancement, flare removal, and we have under-display image enhancement. All of those problems can benefit from the linearity in the raw image, right? But they just decide to work off-camera ISP to avoid all of this kind of camera-specific things. And one of the work I worked on was post-capture exposure correction. And it's very simple. Just let's generate a data in the right way that very close to what happened to camera ISP. Then once we have the data, let's fit a neural network, train it, and that's it. So we just generate a bunch of images with different exposure, like darkness and brightness levels, and go through a software that mimic the camera ISP. And then we have a ground truth that represents the best exposure settings. And then we just train a network, right? And we can go from this image on the left to this image on the right. So that's great. Most of those solutions kind of plug in and play, generalize very well, right? And doesn't have this kind of camera-specific issue. But it cannot handle every case because we already lost a lot of information during the camera rendering, right? The camera ISP produced the final image, but also throw out many of the information. So if we have a look into what we called color gamut, or like the possible color that can be represented by any color space. So here is the color space that can be represented by the linear representation of the image in CIE/XYZ space, or any other space will be similar, versus the standard RGB of the final JPEG image. Like this is the JPEG or PNG images we used on most of the computer vision applications, has this kind of color representation versus the linear one. And of course, during the camera rendering, we go from here to here, and that's what we call the gamut compression. And that means we lost a lot of information, right? So losing a lot of information, meaning, for example, image like that, if we would like to enhance in post capture, we cannot do anything with those areas, right? Like we have this halo artifact, and we couldn't do anything here because we don't have any information, right? And second problem in the camera ISP is the non-linearity introduced by the steps happened in the camera ISP. So we have this kind of global like tone mapping and local tone mapping and lookup table. All of those processes change the linearity of the raw image and give us a final good image, but we cannot fix errors in this after this non-linearity in the same way. So for example, let's go ahead.
The values for the hyperparameters, like for example, when you trying to remove overexposure,
Okay.
isn't it like skin tone dependent for people or just
Can be.
color dependent
Can
for
be,
different
can be.
objects?
Yeah, I mean, like I didn't discuss any algorithm for exposure adjustment during capturing, but yeah, you are right. Like it can consider some semantic information. It can just consider signal processing, like pure signal, like what kind of the histogram, for example, of the image. And there are some rules, like we try to make sure the brightness level has this kind of like scheme, and based on that we adjust the exposure, but all of that during the ISP, right? Once we capture with a problem, we will stuck with this kind of images. Yeah. So yeah, we have nonlinearity, and let's take this image as an example to discuss how the nonlinearity impact us. I should go faster. So this image, of course, has hopefully you can see that, but it has a problem in white balance, right? Like it has a bluish tint that is not natural. And let's do the correction on post capture. And this is the one of the work I worked on. I think was my first paper in my PhD. You can scan this QR code, and for all of the other work I will discuss to see the GitHub page. So yeah, let's go with this. And I will manually select a reference point, white one, to represent like what kind of bias in this image we try to remove. So this is the best case because there is no estimation. I just manually I select a good reference point. And let's do the diagonal correction, similar to what happened to the camera ISP, right? Like during the camera ISP. And it's good. But as I said, to appreciate how bad or good it is in colors, we need to see the best version, right? And compare. So this is the best version. I hope you can see the differences. So this is the same image, but if we render it through the camera ISP with the correct white balance, right? And on the left is the best case we can get ever, but in post capture. So why we couldn't do that? Because of the nonlinearity, right? Like the assumption of the diagonal correction is broken already. Okay. So what we propose is just to simply replace the diagonal correction one with a nonlinear correction function. That's it. So let's assume we have a ground truth image in sRGB, like after the camera ISP render, and we have input image that has some errors in white balance during capturing, and we try to map the color from here to there. We can simply project the RGB colors of the image into a higher dimensional space, like polynomial kernel, and then we just fit polynomial coefficient matrix to map from here to the RGB of ground truth. Just very simple. But in reality, we don't have the ground truth, and our goal is just to predict the mapping function M, right? So it's just a learning based, like not learning based, data driven approach. So we start by building our data set. So we start with raw images, render it with different white balance settings, through camera ISP or like simulators that mimic the non-linearity of camera ISP. And that give us the same image, but with different white balance settings. And then we have a ground truth with the accurate color. And that give us 65K images with different white balance settings, most of them incorrect. And we, for each pair of images in training data, we compute the matrix that we try to predict. And each image is represented as a histogram feature because we don't care that much about the semantic information. And then we project that down to 65-dimensional vector using PCA, very classic. And at inference time, we do the same. Given an image, I don't know anything about the camera pipeline of it or the white balance settings. We search for histogram, sorry, we create histogram, then produce that with PCA, and then we search for the nearest neighbor feature in training with the assumption that if you are similar to me in colors, I will use the same correction matrix, right? Just KNN method, and this is the result. So we compare that with diagonal with the best manual correction versus Photoshop correction. And this is our results. Lower is better here. So all of this, those matrices are errors, like mean square error, mean angular error, and delta E. So you can see like we got way better results than the other alternatives. And here is a qualitative comparison, input image, Photoshop correction, diagonal, this results, and the ground truth. So yeah, that's simple, very straightforward, but just like, yeah, go ahead.
Sorry, quick question. So the manual correction comes from your ground truth color
Chart.
your
Yes.
color chart.
Yes.
Okay. So you're adjusting manually to get exactly the color that you
That's the best
that you know, of
option.
course,
Yeah.
and that's what you consider to be your manual correction.
Exactly. Yeah. Like for each example, we start from raw, right? So
sure.
to get the ground truth, we manually select a grayish patch, so
Yeah,
that
sure.
reflects the light, right? And
Yeah.
in testing, when we compare with the diagonal, we use the same patch here, but apply that in sRGB. So this is the best case.
Okay, I was wondering if you were referring to manual correction as someone manually correcting.
Oh, no.
No. Well, I just wanted to be sure. I
Yes.
see what part you're doing. Okay.
Yes, yes. Yeah, thank you. So, yeah, of course, we can replace all of that with a neural network. So that's what we did in CVPR 2020. And just unit, give me the data we have, input different white balance settings, ground truth. But we can do better. So instead of using that for correction only, we can do that for editing. So instead of just do the correction, like the trying to completely remove the color bias, maybe we can include some user preferences, right? So we attach different decoders and train a single encoder, multi-decoders. Each of them has a specific target white balance settings. So we can do the editing in post-capture that similar or maybe closer to what we can do in camera ISP during capturing, right? So we start with this image. Here is the result of auto white balance correction, and here are different user preference rendering using different decoders. Here's a comparison between, at that time was, I think, good devices, like iPhone 8 Plus photo app autocorrection, Google photo app photos autocorrection, Samsung S10, and our results. And we have a GUI. You can just like white balance the image, select any other images, and manipulate that interactively. Maybe I can. Yeah, just wait a second to see that. You can just white balance it, and then you can adjust what we call color temperature, kind of like if you go lower, it's cooler or bluish. If you go higher, it's warmer or reddish. So yeah, to conclude, working on off-camera ISP in post-capture is making things more general or like less dependent on the camera, but less effective compared with working on RAW, like which is linear representation of the incoming light. and add more challenges to the task. For example, like comparing the simple diagonal versus what we done to achieve something closer to what we can do with the simple diagonal correction on camera ISP. So I will go very fast on learnable camera ISP, and back again to the idea of working on standard color space or off camera ISP. So the authors of Learning to See in the Dark, which is very popular paper in the low light image enhancement, yeah, they decide just to do the other way, right? Instead of working on sRGB after losing all of the information in dark images, let's do that on very early stage in the linear raw images, right? So they propose to have a neural network start from the mosaic image, right? Like this one in the early stage in the camera ISP. And let's fit a neural network to give us the final image that looks very good, but captured in a very dark lighting condition scene. So you can think about it of this as camera raw space, like working in camera raw space or being camera specific model, because if we change the camera, we need to retrain, right? There is no way to reuse this network. So, yeah. And this introduced the idea of replacing, go ahead. Oh yeah, because we have usually in this kind of color filter array, we have double greens versus like you have here green and you have here green. So you have double greens versus the red and blue. Yeah. So we have two greens and one blue and one red. Yep.
Mahmoud?
Yep.
Yeah. Just a question there also. When you train on raw space, do you observe the same early features in the network, like the age-old Bayesian filters that we observe?
This is not my work, but yeah, I think it's different because it's completely like it's not like trying to recognize the objects. It just try to process the colors or removing noise.
I'm wondering if there is some kind of transferability between an RGB network and a raw camera network.
Yeah, it will be great, but like I don't know. I didn't see work doing that, but yeah, it's a cool idea. Yeah. So basically that introduced the idea of replacing the entire thing with a single neural network. And since that time, we can see different papers, every one with different architecture, maybe loss functions. I will not go into details, but like many, and even challenges, making things invertible, going back and forth, and so on. So to conclude, the scheme is that we have a camera, and let's think from the manufacturer point of view, right? I have a camera, and I would like to use the camera ISP, the learnable camera ISP, I mean, and what I should do is I have to collect a paired images, right? So one from my camera, raw space, and one in the target color space, sRGB, like one of the standard one. And usually I will use a higher quality camera, right? Because if I use the same camera, then that means I already developed my camera ISP, then why I wanted to learn the camera ISP. And then I train a neural network. But then I will have another camera in the same device. Usually comes with new camera response function. So I cannot use the same data. I need to collect another data set. And so on, right? And keep in mind, like manufacturer usually like release maybe 3 devices per year, every one with maybe new camera, front camera, rear camera, etc. So it's a lot of work. And we, like users, sometimes complained about specific aspect in the images. Like for example, here, user doesn't like the fact that the white balance remove this orange tint, right? Like we would like to keep that. So that's usually in the behind the scene, we file a bug and we try like as a software engineer to fix that, why that happened, right? And maybe they don't like the photo finishing part, or maybe like some user found the camera introduced teeth to their baby that doesn't exist in reality. As another user hate the super resolution in Google Pixel. So every part of that is a specific module on the camera ISP. And behind the scene, we just like like pass this bug to the responsible team and they try to fix that. But in Learnable ISP, the idea of replacing everything with a single network, that's kind of impossible, right? Like you cannot control how the network will behave in a certain aspect of the image part. So that arises a question, can we replace camera ISP with Learnable one or not? Given the fact that it requires training or tuning for each new camera, and that means we collect a paired data for each new camera, very hard, and difficult to control and debug compared with the conventional camera ISP. So that takes us to the final part, which just some thoughts about how we can make this idea of Learnable ISP more practical, right? So just focusing on two aspects. The first one is row-to-row mapping, and we try to think for a solution to solve the problem that trained Learnable ISP on camera X cannot work with images taken by camera Y, right? And the second part is the decomposition and the modularity of camera ISP. So it's very important to keep that because most of the current Learnable ISP are black boxes and cannot be controlled or like hard to debug. And I will just conclude with insights and future research. So let's start with the row-to-row mapping. It's just domain adaptation, very simple. Instead of go directly from row to whatever we trained on camera A, we just introduced another step taking us from the new camera to the space of the old camera that used for training, right? It's just a domain adaptation step. So, of course, if we will follow learning-based scheme, it will be a very, maybe not very, but not a cool idea to say, okay, let's collect a paired data to go from camera A to B, because if we will do that, let's do that and train the ISP, right? So we need a practical solution to map from raw images of camera A to B, and that was the work that we proposed in BMVC 2021. And the idea is to trying to map the raw images from, let's say, iPhone to looks like the raw image of Samsung, such that when we render that through Learnable ISP trained on Samsung, that give us sRGB images looks similar to what we get from Samsung device. So just like practical, we need to do that in practical way. So we propose a semi-supervised row-to-row mapping method, and the idea is saying, okay, we need a bunch of images, unpaired images from two cameras. It's very easy to collect, right? Just open your camera, capture random images by each camera. And we need a few paired images, like 20 images, something in that range. And we have a very simple encoder-decoder scheme. So we take images from camera A, go through encoder-decoder and do self-supervised or unsupervised reconstruction. So just trying to reconstruct the image from A, from the input to the output. The same for the camera B, right? But if the training example coming from the paired set or what we called anchor set, then we try to make whatever the encoder produce similar to the encoder here. So that means at the end of training, the decoder here and here will learn to take the same input, but produce the image based on the configuration of the target camera, right?
Do you need any permission from Apple, for example, for Samsung to be able to do that based on their work?
Yeah, so that's a cool idea. We didn't do that, but it's very cool idea. Like it should be considered. Like if we consider any information from the camera model itself, that will help. I will discuss that later. But like, yeah, it's in the future. Like it's insights. But yeah, like in this work, we just treat it as an image-to-image transformation without any knowledge about the camera, which is not great. And then at inference time, we just swap the decoders, right? So just go from here to B and from B to A. And we be able with that to take images from iPhone, map them to Samsung, as I said, and render with ISP trained on Samsung. Versus if we take the same row without any mapping and then render that directly with Samsung. Then later, I was just one of the last names in the paper. I didn't contribute that much, but all the work done by Georgie, accepted by ACCV this year. It's a fully unsupervised framework to do the row-to-row mapping. So instead of this kind of anchor set, just like as based on cycle GAN scheme, with some tricks here and there, we got to do that with a fully unsupervised scheme and achieve better results than the BMVC work here. So here is the big improvement in BSNR. So very fast. The second part is the decomposition and modularity. So instead of having a single neural network, how about we think of having different neural networks and each one just focus on one of the aspects. But if we do that, we need to consider the fact that we try our best to make that module less dependent on the camera, right? Because otherwise we need to collect training data for each new camera. So I will take again the illuminant estimation as a use case, and this is the typical scenario. If we go with training-based illuminant estimator, we have a model for each sensor. That means we collect new training data for each sensor. That's not accepted. So this work, ICCV 2021, we propose a simple idea that saying, okay, we can on the fly produce a model weights that can work with the testing camera instead of just having a single model trained on some cameras. We can learn to produce a camera-specific model on the fly, right? So the idea is, let's instead of relying on the input image, let's try on the input image and additional images taken by the same testing camera. And the idea or philosophy behind it is let's give the model some information about how the color can be produced by this camera, right? So it built on the top of one of the popular framework in illuminant estimation field. It's called convolutional color constancy by Jean Baron. So the idea of convolutional color constancy is that we take the input raw image, we compute a histogram feature, and we learn a filter in frequency domain, like just a convolutional filter, single convolutional filter in frequency domain. That convolve over the histogram, then we add a bias and then compute a softmax. This is just like a very simple, poor description of the method, but it ends up giving us a heat map about the likelihood of the illuminant color bin in the histogram space. So where the most likely location of the color, the lighting color in this space will be the maximum value here or the average or whatever. Then we can project that back to the RGB to collect the image, right? This is the convolutional color constancy. It's a single filter for each camera because of the same problem we mentioned. So it's very simple. Let's take the histogram and the histogram of additional images randomly taken by the same camera, feed them to a neural network to produce the filter and bias on the fly. So just like the neural network will see several examples and then will produce what is the best bias and filter. Usually the bias is the problem that can work with this inquiry, this query histogram. So we got the state of the art with very small model size. It's just 1 mega. Of course, this is numbers like you never see in language and vision, right? Like 2 megabyte model. It's just like nothing. But that's very important because of the natural type of the problem. So like it should be very fast, very limited, require limited resource to run on devices. So the last part is, let's, instead of trying to focus on each block and replace that with a neural network, let's keep do like a hybrid method. Let's keep whatever conventional parts as it, and let's just introduce a neural network to do the photo finishing after going to some of the standard color spaces. And as I mentioned, one of them is called CIEXYZ, and that was the work we proposed here in TPAMI 2021. And the idea is trying to unprocess the images in a more advanced way than the simple MATLAB function or OpenCV functions, such that we can get something closer to the linear representation of the images. And we do that in the opposite, like in the opposite direction to render them back. So the idea is, let's start with some images in sRGB spaces taken by different cameras. Sorry. Let's start with different sRGB images taken by different cameras, and we generate like the linear representation of those images, but in the standard CIE-XYZ space, like one of the standard spaces. So we can learn to map from sRGB to CIE-XYZ. We divide the problem into local mapping that represent any local adjustment that may happen in the camera ISP, and global mapping to represent any global color transformation happened in the camera ISP. And then we do the same reconstruction or forward pass, and that trained jointly. So here's an example. This is the input sRGB image. Here is what we produce as a local mapping layer. Like this represent whatever happened from the local tone mapping or anything, adjust the image locally. So we subtract this from that, I don't know. But like we get this, and then this is the global mapping. This is the ground truth XYZ image, linear one, and this is the forward pass. It's useful for different applications. So in sRGB right now with this, we can do better white balance manipulation in post-capture time. We can even do different low-level computer vision tasks in better ways. Like, for example, here, dehazing in sRGB image. So this is sRGB image. If we dehaze that directly versus dehazing that in the reconstructed linear image, then we render that back, we get this result versus this result. The same for low light image enhancement. Here is the input images, and here if you apply whatever algorithm we used to do image enhancement in post-capture, versus if you do that in linear space, then re-render. So you can see the noise level, you can see the differences in details. So the insights and future research based on this discussion is row-to-row mapping, and we, like, as discussed, like we didn't consider any of the phone information or the camera information in the solutions. So I think it will be great to incorporate camera response function, for example, to do better row-to-row mapping and decomposition and modularity. So breaking the camera ISP into steps better than just a single block. So maybe it can be a camera-specific modules that require a little bit of tuning maybe, and then we have non-linear plug-in and play photo finishing part. I think that will be should be the next step if we do research in this topic. And of course, the work I discussed was done with amazing researchers and engineers. And that's it. Yeah, thank you.
There are questions already. You had. Yeah, you go.
Well, thank you very much for this presentation. I know that you covered a lot just regarding, color correction, but I would like to ask about the method utilized, like for example, for enhancing the quality of images. For example, for the case of distorted images, especially like one of the cheapest cameras available for prototyping is fish eye lenses or cameras. What are, like, for example, like the very classical method that is used for camera calibration is the checkerboard, like to do the camera calibration. But I would like to know what are the most advanced, methods that are used in this case for distorted images.
So basically, we have like seen papers that focus on like image deformation, like based on any distortion happen from the lens. And you can even observe that if like you compare iPhone versus an old iPhone maybe, or Pixel versus an old Pixel, like in selfie pictures, like usually the face should like looks bad than what we see, you know. But like, is there an advantage to do stuff in linear space versus sRGB for this problem? Uh, I don't think. Like I think like whatever people doing in post capture is good. I don't see any advantage of using linear input versus the nonlinear here, because we are talking about the structural information rather than the colors. And but yeah, I mean, like, why we do that in camera ISP? Because we do that because we render the images, so it's part of the job. But maybe they apply that even after finishing the pipeline, right? So there is no advantage, I think. Hey, that answered the question, or you are asking in general, like what the latest? I didn't work in that to know. Sorry, but yeah, I just like use the like what I learned is just like the classical thing in computer vision, like the MATLAB toolbox. Yeah, this one. Yeah.
Cool. Thanks for the great talk. I have two questions. One question was, so you at some point had this part where you learn these individual matrices with the pseudo inverse stuff,
Yep.
which basically is like depending on the scene, I think.
The color chart, right?
Yeah. Is it like, what are we talking about? Like a million of these, or like 100?
Oh, just
tens,
like
or...
no, like 10
I
maximum,
see.
something like that. Yeah.
And then the other question was, I didn't quite understand it. So the XYZ space is like a subspace in this
And this
visible color spectrum?
triangle, okay. So basically, this one is just showing the XYZ space. So
Yeah.
this is the XYZ.
Yeah.
Like the range of values that we can cover in RGB.
And sRGB is the triangle.
It's a subset. It's a subset of it. Yeah. And
Yeah.
this is like whatever JPEG, PNG, and like all the what we used mostly in that, unless your image was saved in something like whatever, like color space by Apple.
I see.
That has wider gamut.
So the XYZ is better for a couple of tasks because it contains strictly more information.
Yes.
I see. Okay.
Yeah.
Great. Thanks.
Yeah. Thank you.
Yeah.
Thanks. Thank you for your presentation. So as a follow-up, I would like to know how like your work is being deployed. For example, is it being deployed into Google Pixel phone?
Never been deployed.
Okay.
I was hoping. it never, because so basically like most of that done before I joined. I didn't discuss anything since I joined. Part of the deployment in general is like it's a very long process, and it depends on the company. Like in Apple, for example, it's when I was working, like my manager told me that if we have a serious failure case, a single one, we kill the project. So there's no option to have a single like crazy example. So there is like are different aspects than just I got the bold numbers in the tables, right? So yeah, it's
And Just a follow-up. So if, like, for example, if this were to be deployed in real life, like where are some of the applications? You talked about the Google Pixel, like the camera, but what are other applications where this could also be useful?
Like the ISP, you mean?
Yeah.
Basically, anything related to image editing and enhancement should start from raw. Like for example, like we have Adobe Lightroom, so just the entire software is based on the idea of give me the raw image, and I will give you some functionality that's not allowed, or you cannot do that with your like other apps, right? And maybe you can ask like how Adobe Lightroom can accept any DNG, right? Like we can take a picture, raw image from Canon and Nikon and upload them to Lightroom, and Lightroom works pretty well, right? So basically the answer will be if you ask this question. Because they do calibration, like they calibrate for each of those steps or most of them for each different cameras, right? So the application is just photo finishing. Some papers discuss the advantage of doing high-level vision on linear space, like semantic segmentation or identity classification. But I saw like some semantic segmentation works that argue if you do stuff early. Another idea I saw different papers doing is instead of training a neural network to generate the final sRGB image that's beautiful for the user, let's tune that to serve our task. So I'm doing, let's say, image classification or like face detection. So let's tune the camera ISP to produce to me RGB images that's better for my network to detect faces, you know. So this is some applications, yeah.
Thank you very much.
Hi.
Oh, yeah, sorry.
I was wondering what kind of okay, so that you can like use an actual camera and get a raw image.
Yep.
What kind of programming language do you use to interface?
Like most of this work, or like the interface to get the raw, you mean?
Yeah.
Oh, the raw, like I don't think iPhone allow you to get what they call the pre-raw or post-raw, something like that. But Pixel, if you have Pixel or Samsung device, in the settings you can just say save DNG file. So this is the raw image. Save DNG. So the format is called DNG. But if you would like to program like an app to doing that, so yeah, I think that's like a function in Android if you are doing Android, or like it's a like an option in the camera, whatever library, or I don't know. I didn't program Android before, but I know it's an option if you would like to have that application caption raw. Yeah, and if you have DSLR cameras like Canon and Nikon, those have the option to save raw as well.
Is the raw also okay? There's .dng, right?
DNG, yeah.
Is also .bmp?
No, BMB is bitmap. I don't know who will save BMB. Yeah, but like I like we use that in a simple like image processing classes just to decode an image and stuff. But I don't think it's a good format at all. But like DNG is very specific for raw images. So it has whatever like the white balance information used during capturing, maybe the noise information, the exposure, all of that is stored with the raw image, the linear one. So, and you can find like some GitHub pages doing how we can extract those information from the DNG file, and then you can start from here. Yeah.
And okay, if you have a .dng file, you can just process it using any language, of course, right?
If you would like to program that yourself, yeah, there is a library called Pyro, sorry, PY, and then raw, Python library. It's just like ready-to-use functions to like do the demosaicing and white balance correction and stuff like that. If you would like to just edit as an end user playing with the image, you can just use Adobe Lightroom and manipulate the image, or Adobe Photoshop. Yeah.
Okay, then just a final question. Okay, if interest in post processing is actually like growing, why not have some residuals of this wasted image from the DNG saved?
Yeah, you can publish a paper with this idea. Yeah, yeah. I mean, like, yeah, there is many ideas. People working in this field in general, like very few. So there is a room to innovate. Yeah. So you can think about like that. Like you can, like, some papers propose to keep some useful information through the ISP, whatever, and then store that as metadata in JPEG image. Like the JPEG has a comment like 65K, allowed free comment. You can add whatever you want. Then you can extract any useful information and then embed those on the JPEG image that you saved. Then you can load them up and do whatever you want, right? So yeah, I mean, like, there's many idea you can try here.
Yeah,
Yeah, thank you.
Thank you. Nice presentation.
Yeah, thank you so much.
I just want to know. I was thinking about it that I will, if I use the SDK for Android or something like this, I will get the image for every single camera, or it's just compressed into a single one.
Like any, I think, yeah, any you mean any single camera in the same device, right?
Yeah. For example,
Like the front or rear or tele or. Oh, any other camera?
there's 3 cameras or 4 cameras, as you said.
Oh yeah, yeah. I mean, like the Android itself, any phone will run Android. The SDK will allow you to do that. Yes, yes. Yeah, yeah. And even in iOS, the programming is available. You can do that, but the iPhone itself, the iOS, doesn't provide that in the native camera to save RAW, based on my last knowledge. Yeah.
The question. I can ask two quick one. One is, I noticed on the metric when you're doing the white balance, you use traditional metrics, so pointwise or PSNR, or this kind of thing. And I was wondering, and there is certainly a reason, but I guess you're never relying on this learn metric, right? LPIPS, FID are not metrics that you use in the field, right?
Yeah, no.
Okay, they are not good for what you try to do.
To be honest, like the current things we have already gone through, pixel-wise, so we didn't think about any non-reference matrices. And usually, like if we are talking about just illuminant estimation, like this part in the camera ISP, we use the angular error. Just we compare the angle between what we estimated versus the ground truth. But if we are talking about the white balance in post capture, this other part, if like this bluish images, so we do PSNR with the assumption that the nonlinearity in the camera ISP may introduce some local differences, because like in general, we are talking on a global white balance adjustment, right? So yeah, that's a part of it. Yeah.
Okay, it makes sense. And another question was related, I think, to what Yuki and Yuri asked. So the information that we're losing by the fact of doing the white balance, right? We're getting rid of some information just because of the encoding after, right? And I was wondering if we have some insight on what are the tasks that are suffering from that loss of information. I'm kind of thinking of all the line of work from Fredo Durand, for example, MIT, where they use all these information, very weak information that we have in the signal of an image or in the raw image data, for example, for reconstructing, or I'm thinking, for example, of vision through particulate weather to adverse weather, because we know we have more refraction from grid lines, this kind of thing that we're losing at the end, right?
Yeah. So basically, like taking the white balance, for example, usually like after every single step, we do clipping. That's like a traditional step in the camera ISP. So for every so often we lose some of the information, like lower information or higher information. Of course, those information are useful, but like how we can keep that, or I don't have any thoughts, to be honest.
And without
unless we keep residual or like any novel idea than what we are doing. Yeah.
And without recovering, do you know, I absolutely don't know that line of research. Do you know if there is a line of research trying somehow to reproduce all the computer vision, but just on raw images?
Oh, yeah. Like, not me, but my supervisor, Michael Brown, already had some papers proposed to store a very lightweight, useful metadata, allow us to reconstruct raw from sRGB, but like not residual. That's why I told him to publish a paper, but like kind of like a small lookup table and stuff like that. But like we don't have, the problem is we don't have enough raw images on the internet to do a deep study on different fields to see which field got benefit from that or not. But in theory, raw is linear is good. So why not? Yeah.
Okay, good point.
Yeah.
Any final question? From the audience? No, then I think we're going to conclude. You had a lot of questions already, so thanks a lot for that great talk.
Thank you.
For being there on site also.